Good afternoon, everybody. I'm glad you guys stayed for the rest of the conference. My name is Jiri Hofman. I'm a radiation effects engineer with Cobham, but I'm also a PhD student, so I have sort of two organizations linked to the Cobham Lab Solution, place in the UK, and the Brno University of Technology, which is in Brno, Czech Republic. So, when it comes to my commercial life, I am with a radiation testing company, so we do all the kind of radiation tests you can imagine, not only for space, but we do also a lot of work for nuclear power and other related businesses. When it comes to space, the key tests we provide are the classical PID and SC testing. Talking about classical way of testing, that brings me to a slide where I'm trying to quickly describe how it works. So we have typically two types of customers giving us the requirements. One type is mission-driven, so it's a typical radiation hardness assurance team of some company designing the mission. So these guys are telling us what they want to test and what are the requirements in respect of the radiation. Second type of customer is a customer who is developing a new component and they want to actually certify it as a red hat or prove that it has some sort of level of radiation hardness. So when it comes to total dose testing, that's a very standardized, very classical test where we do through a loop, we reduce some certain level of dose, we test the part, if the part is happy, we continue the test, if the part is not happy, we stop. When we reach some certain dose, we let the parts anneal. We report the tests, we report the test results to the customer, and job is over. It's a typically component level test. Similar story would be the single event testing, which is significantly more complicated when it comes to the preparation of the whole system, because while the PID testing could be done the way that you irradiate and test, here you are irradiating and testing at the same time, so it's an in-situ in-beam testing. So there is typically a prepared PVP for the mounted on a PCB, and the whole thing is exposed to the radiation, and the single events are observed live during the test. So this is really standardized process. There are European, American standards everybody is using, and it looks like that I'm done for today. But there's a lot of limits and a lot of challenges in this classical way of testing. So basically, we have limited access to the radiation sources, not we as a company, but we as a mankind. When it comes to total dose, every large test supplier like us has their own radiation source. We do have one here in the UK. But when it comes to single event testing, we are talking about accelerators, and there are really technically a few worldwide. So there are maybe 5 facilities across Europe. There are 2 in the US. Then there is something going on in Russia and in China, and that's the whole story. So it's a challenge actually to get in time. It's a challenge to synchronize everything with the customer. That's one problem. The other problem is that actually we are always assuming, we are always making a lot of assumptions. We are always simplifying the space environment, the real radiation space environment, into something simple we can generate on Earth and test. So we are not really testing against the true space environment. That's a one big question mark. Another challenge we have is that we typically accelerate the test, and we accelerate it a lot, orders of magnitudes, 5 orders of magnitude. No problem, we do it as a commercial service, it is required by the customers. The question is whether what we call dose rate effects are actually killing the test or not. The standard allows you to do that. It's a perfectly fine process, but the question is whether at the end of the day, if you in 2 days irradiate something simulating 30 years of operation in space, whether these two things are the same. That's a never-ending question mark we are trying to answer. When it comes to the testing, most of the test houses like ours have what we call test libraries. So we have actually some classical standard components already tested 100 times. So if a new one comes, we just like to modify the parameters and we can run the test. But when it comes to new technology, companies developing new microcontrollers, for example, like we have to develop a new test from the scratch. And it's a lot of work, not only in hardware, but there is a lot of software also involved. Now, the complexity of the devices is growing like crazy. This is out of control, actually, I would say, with respect to testing. We just recently had, for example, one customer, they came with a microcontroller, he said, okay, what do you want? There's a data sheet. He said, okay, it's got 1,500 pages. So we will be testing this for 47 years. So that is not acceptable. So this is one of the challenges we are facing nowadays with these advanced, especially commercial parts. Another serious challenge is actually the preparation of the samples, because when it comes to single event testing, you have to actually prepare the part, which means you have to remove the lid and you have to thin it. Sometimes. The reason why is that a lot of the accelerators we have, and we are not really allowed to use them, unfortunately, have very limited penetration of the particles. So actually the devices, even the silicon thickness of the die, are too thick, and the particles are not penetrating the die where the sensitive part of the chip is. So you need to open it and you need to thin it, and you really mechanically thin the devices. So you can imagine that this is really not a simple process, and it takes time and it costs money. So that's another bottleneck we have on the standard test. And the final one I would like to mention here is what we call bias, because during the irradiation you are running the device under some conditions. They are biased under some conditions. It's a very important thing, because if you change it, the results will change. So the bias conditions should be right during the mission. But if you are testing on the component level, particularly for somebody who is in general interested in the component behavior and wants to use it in some database, then they are also using very bias conditions. So that may have a serious impact on the true operation of the component in space. The same story is the timing of the device. So it really depends what sort of clock frequencies you are using. So what can we do about this, and what is the result of this? So this standard testing takes a long time. It's component level focused. So at the end of the day, the costs typically of testing some advanced components would be typically a cost of a typical submission. So this is really another solution for missions like you guys were talking the last 2 days. So what we can do, instead of doing component level tests, we can go to the system. So we would irradiate and test the whole board. We would irradiate and test the whole satellite. Why not? We can do that. We have facilities which are big enough actually to accommodate the whole satellite. And then the testing is done during the irradiation. The satellite can test itself. So just by modifying the software, the job could be done on the system level. We can combine this sort of self-test with some external data acquisition system, which is outside the irradiation area. So it's independent. So if you have this classical situation that some part of the satellite reports that the other part of the satellite failed during the test, you have an independent system telling you what was the truth. And that allows to significantly speed up things and, of course, reduce the cost. this, what I just said, is perfectly applicable to the total dose testing. When it comes to single element testing, again, the challenge is the penetration depth of the beams. So we can do both level, for example, on high energy protons, but we would hardly do satellite level on high energy protons. When it comes to heavy ions, you can do boards, but again, the parts must be delivered, must be thin in many cases. So there are limits. But just recently, within the last couple of years, there is an effort actually to develop new facilities where the energies will be significantly higher. And one of them to mention is actually called CHARM, and it's been built in CERN, and it's using one of the fantastic sources we have there. So that allows actually the whole satellite really to be tested. So we still have the challenge that actually we are still using some simulated radiation, which is not exactly what's going on in space. So the best way to test what the space radiation do is to do it in space. So so we've been also studying the method for doing radiation testing in space, which seems to be a really good match with CubeSats, because CubeSats are small, relatively cheap, relatively fast to develop, relatively fast to launch, which may not be the case, but it's an ideal platform. So what if we test those things in space using the real space environment? We can do that, but again, we have some limits. One of the challenges here is the dosimetry. We assume that the satellite had received some radiation during the mission, but really to do a good test, we need to measure. So we need on board good dosimetry system telling us, okay, this is the amount of radiation the system had received, and this is what its results should be linked to. The other challenge is that, say, we have in the CubeSat one payload card with the system under the test, then we need something around hard which would actually be able to test that and say, okay, we have payloads like that, like this. And in space, we have no method, no basic method actually to recognize which of those two systems is reporting to the temperature than it had actually had. So that's another challenge. But to conclude this introduction part, the standard methods are really in practice limited for CubeSats, and it's mainly due to time and cost boundaries. Otherwise, it's perfectly fine. But the money is really killing this approach. So if we go to system level testing, and that's what we are actually doing with the CubeSat customers, we can significantly reduce the cost, and the CubeSat customer can still understand that their system is okay, or there is some significant problem they should really avoid, so they don't have a mission fail. So let's move on to my second role, which is my PhD, so now I can take off the business jacket. Talk about some research I've been working on. So my PhD is actually linked to my previous background, which is meteorology. So I'm actually a guy who is measuring things. And so I said to myself, okay, so let's measure in space. And let's measure in space with the same accuracy I used to measure things in the industry. And because now we have this classical problem of the industrial electronics and commercial electronics to be super advanced compared to the space stuff. So I asked myself, okay, so is there any way to bring it close together again? So the idea here is what are really the showstoppers? Is it the fact that the radiation would actually cause a mission failure on such a system, or is it just the fact that the radiation would do some degradation of the performance of such a system? So to do that, I tried to develop some advanced test technology actually allowing to measure these things on the ground and potentially fly one day and see what happens in the real space environment. The overall idea is that if we fly it, and we can fly it, and if we model the radiation-induced degradation based on the ground testing, we can, in theory, like during the mission, do estimations what is the degradation of the system. So let's make an example. You have an instrument measuring some property or something, number of the fish in the Europa's ocean, that would be the nice one, right? And there is a data acquisition system on it. So this system should be able to, using the data from the onboard dosimetry, it should be able to estimate, okay, at the beginning we were measuring plus minus 1%, now we are 100 kilowatts into the mission, and we are now 10% on the accuracy budget. So I work on that. I spent a couple of years developing these things. A lot of stuff has been published, and now I would like to present you the final stage of my research, which is an in-orbit experiment. So I have developed a second generation already of a very, very small payload, which can do all the job I mentioned in the previous slides. So it measures the radiation, and it measures degradation of some high-precision analog to digital converters, some very high-precision voltage references, which are used as a standard for the measurements on board. And it can combine all these things together. So actually, it tells you that we have this sort of dose received, and we have degradation like that seen on the parts. So, so the core part of that is a advanced radius technology, Texas Instruments A2D converter, which actually has most of the needed facilities on board, including the 2 A2D converters, some very, very nice internal self-test capabilities, and it also provides all the driving signals necessary for measuring the radiation with rack pads or PMOS structures. So if you look on the block diagram of the system, it actually consists of the part which does the dosimetry, so that's the rack pad and the PMOS structure. These guys are also quite temperature sensitive, so a high precision temperature sensor is added to the system. The key factor of being able to say what is getting more or less radiation sensitive during the mission is to have something which is radiation tolerant. So actually I'm using some special reference system here, which is radiation hardened by default. And then I have a bunch of voltage references in the system, which can actually work the way that they cross-compare each other, or the system cross-compares their voltages. So actually, you can analyze the ratio between them, and they are known for being in some way radiation sensitive. The rest is done on the chip. So the chip has 2 A2D converters, as I mentioned. It has also current D2A converters, which are necessary for driving these radiation sensors. It has also what's called TDAC, which is a fast digital to analog converter. So actually, this guy can be used to test these 2 guys. So all in all, the system can really solve the equations, one equation of 2 variables. In fact, because it has a lot of cross-checking capabilities, which allows to understand actually very true radiation effect is within the system. The idea is, if I go back to the introduction, is that this is completely developed as a box, and the CubeSat missions will be provided with what I call a Radex package, which consists actually of a schematic, and list of parts. You need to integrate the system, so you can hook it up to your hardware and basically a PCB. Then components for the flight model will be provided by myself. Those are components from the lots. I'm doing the radiation testing on every moment. And there is a lot of software actually to operate the system, so there is a SQL package which is also provided. So actually, this system can be very easily integrated with the CubeSat. When it comes to the mission itself, then there'll be a lot of binary data provided through the telemetry, which I will be analyzing, and thus actually seeing the results of this experiment. So I had already successfully integrated this design with the first CubeSat. This is an Italian project called Haze. I hope I pronounced it properly. It's a 130U CubeSat, which is basically a topological demonstrator. It has a bunch of telemetry systems. Interesting architecture using just a very standard low power SD microcontroller. Everything is on a single board. So actually inside this little cube box there is one PCB where all this stuff is placed on, and it has a DCS system based on magnetic purpose. So they will be hopefully able to do nice orienteering of the satellite, so the camera can point roughly at least some place they want to shoot pictures of. So technological demonstrator basically to look what the satellite system cannot do. It should be launched mid of next year to a polar orbit, which is very important information for the radix experiment, because to understand what sort of radiation this experiment could and should see in space, we've done a bunch of simulations using Stanis and Omer. Here you can see actually a total mission dose in kilorats versus the aluminum thickness of the overall shielding of the electronics. So we should be somewhere within this box with the satellite. So that says that for 1 year mission, we have something between 20 and say 6-ish kilowatt. So that should be the range of doses we should see. These simulations are taken to be rather pessimistic. So I'm also using published data. So this is an example from a very nice conference which was organized by CNES last year. And their practical experience is that when you are inside a satellite, inside the aluminum shield, you should see few kilowatts on such a mission within a couple of years. So few is for me, say 5. So I said, okay, so I will design the thing for 5 kilowatts. So the experiment, the experiment is now completely developed, and I am through the final stage of doing the radiation testing. So as we speak here now, there is a demonstration experiment running with these parameters, where during 1 week I will actually simulate the 1 year flight. This is how it goes. So technically the experiment itself is just this piece of hardware. The rest is an external hardware which is doing the external data acquisition. So this is actually providing signals to external bunch of instruments, including a very high resolution multimeter. So I could actually compare the data measured on board by this A2D converter with the data from a very high resolution system outside the radiation facility. So this is one of the results just quickly. This is the dosimetry system. So this is the irradiation started at the time 0, and you can see that there is a really nice response of both the RADFED system and the PMOS. There is a slight nonlinear response on the RADFED. That's a quite common problem. Here is what we should see on the voltage references. So actually, because this is not an absolute system, this is using relative comparison of these measurements. So this is showing the ratio between those references, and here this compared actually with the A to D converter measured. This is the blue line with the red line, which was measured externally. So you can see that there is a very good agreement up to some moment where some dose was reached and something started to going on in the system. And this is the final chart where actually the A to D converters themselves are being tested against each other and against the test source. The second A to D converter was perfectly stable, but the primary one was actually showing some two trends here. The blue, the beginning, this linear trend down here, is actually a temperature effect. It's not the radiation. But from this moment on, this is truly a radiation effect, and that is in very good agreement with that chart actually on the previous slide. So actually, this is proving that the HD converter from some certain dose starts to degrade. So this degradation curve actually can be measured like in space, which is exactly one of the objectives of this experiment. So to conclude, the radiation test technique has been presented. The in-orbit experiment was developed, and it is ready to be integrated with any mission which will be interested in this technology. So we shall have first data available at the end of next year, but the package I mentioned earlier on is already ready to be integrated and supply. So if you guys are interested, please contact me at my email. There's also a bunch of papers available on the IEEE or on the email request. And with that, thank you very much.